welcome everybody on our Thursday seminar. So today we have a pleasure to host Frederik Wilde, a PhD student from Freie University in Berlin from the group of Jens Eisert. And Frederik will be talking about a very exciting topic, namely stochastic gradient descent in the context of hybrid quantum classical algorithms. So this is a topic which is very, let's say, close to my heart and heart of some people from the group, because we are interested in this NISQ regime, NISQ approach to quantum computing, where you don't have fault tolerant computation, and you have to resort to some kind of heuristics that hopefully work in the, let's say, imperfect hardware that is available in the near term. So this is what Frederik will be talking about today, I guess. So I'm very excited. So please start.
Thanks for the introduction, and thanks for having me. I'm happy to talk here, and I am going to talk about our recent findings and results from our recent paper, which you can find here on the archive. And I also uploaded the slides here to my website in case you want to look at the references later or the slides themselves. So because this is, I was told that there will be a somewhat broader physics audience, so I'm starting with a slight introduction and say what I mean with hybrid quantum classical models or hybrid quantum classical optimization. So, okay. In all of these methods, we have two parts: the quantum and the classical part. And in the quantum part, we have some quantum computer which applies some quantum operation to some initial state and produce an output state. And this quantum operation has some degrees of freedom, some parameters, theta, which specify the particular circuit that is applied to this output state. And then this output state, therefore, also depends on this parameter, obviously. And this could be a high dimensional vector. So this could be many parameters in case you really don't know what your optimal operation is. And then you have to optimize all of these parameters. And how do you do this? Next thing that happens is the quantum computer performs a measurement according to some observable h, say, and sends this measurement results or several measurement results to a classical computer, which then calculates some loss function. And this loss function then also depends on these parameters, of course. And I've already written down the expectation value of our observable h that we are measuring with respect to the output state. So in general, we are interested in expectation values. One might also imagine working with the measurement results themselves directly, but in general, we're interested in things like energies, and then we have to operate with these expectation values. And then on top of that, one might imagine that we don't have just linear functions of these expectation values, but actually non-linear, so any kind of functions, and I'll come to that later. And then what we are interested in for the sake of this work and this talk is to minimize this loss function, but obviously you could also write down a maximization problem. All right, I forgot to mention that. So for this talk, we mainly talk about pure quantum computation. So we ignore all decoherence and noise effects in the sense that we don't model them directly, but we also always keep in mind that hybrid quantum classical algorithms often are designed or devised for NISQ devices. So we kind of have this still as a mindset. We know that this object here is not and has not unlimited power, so to say. Okay, so next thing, once we calculate the loss function, is we use some classical optimization method to calculate or predict some better set of parameters, theta t+1, and then we send them back to the quantum computer, and the quantum computer performs another quantum computation and measurement, and this loop continues until we hopefully reach some set of parameters which prepare a state that's in some sense interesting, gives us the answer to a certain problem. Okay? And then many of you probably know the most prominent example of this is the variational quantum Eigensolver, very inspired by the variational principle of quantum mechanics, where you really just use a quantum computer to prepare or to try to prepare the ground state of some observable or Hamiltonian typically. So this could be some molecular Hamiltonian, and then you try to prepare the ground state of this Hamiltonian by minimizing this loss function. Okay, and then the other canonical example is the quantum approximate optimization algorithm, or QAOA, QAOA, which also goes by the name quantum alternating operator ansatz, so it becomes a little confusing sometimes. And here we have a more specific ansatz. So here I just wrote down this parameterized state psi, but here the state is obtained in a specific way. Namely, we have these two types of gates, e to the minus I parameter times Hamiltonian, and then e to the minus I parameter times x, where x is this this transverse field in x direction. Okay, and we apply all of this to the uniform superposition state, so all qubits pointing in the x direction. And then we have these parameters that typically denoted betas and gammas. So I didn't write theta here, but it's really the same idea. Okay, I'll also come back to QAOA later. Okay, before I go on, maybe let me also reiterate and feel free to interrupt and ask at any point, or say, like if something's super boring, then I can also skip some things. Good. So then, why are we interested in these hybrid methods? What's the motivation? They've been quite prominent and popular over the recent years, and I think for some good reasons. So one of them being is that I think the intuition is that if you do it correctly, you can offload the hard part of your problem that you're trying to solve, that's hard for classical computers, onto your quantum computer, while everything else really can be done by the classical computer. And I think this is the mindset of these hybrid methods, that the classical computer really does most of the job, except for that part that's really intrinsically quantum, so to say, and then this part has to be done by the quantum computer. Yeah, and then I mean there's this similarity or this inspiration by the variational principle, which has a much longer history than all these quantum algorithms. We can tolerate quite short coherence times because we iterate through this optimization loop. So we only have to be able to prepare the state as long as we can run circuits that are long enough to prepare the certain states. We're totally fine. We don't care what happens afterwards in the quantum computer. And lastly, there's this intuition that the classical optimizer will somehow account for errors that your quantum device makes. So either imperfect implementations, control errors, or even noise and decoherence. To which extent this is true and is really working is another question. There's been some very recent work on using like sort of sophisticated machine learning optimization to actively mitigate errors, but I think the general intuition is also that like any optimizer will implicitly drive away from parts where your quantum computer does not what you would actually expect it to do. Okay.
So then, sorry, Frederik, can you comment on this last point? I know it's not like your work, but so you mean, okay, it's actually quite interesting that you can have some form of error mitigation implicitly in this in those schemes, but is it like for some restricted like error models, or just does it work universally? Yeah.
I think I'm not entirely sure. So I think, I mean, if you're referring to this specific reference, I think they really look at specific error models and then decide what kind of optimization is suitable to account for these errors. I think, yeah, other than that.
Oh, sure. Come on. This is a paper from this month, right?
Yeah, yeah. I just read, like, during your answer, I managed to read the abstract. And those people say that they construct circuits resilient to a fine-grained noise model derived from gate-set tomography on some superconducting devices. So apparently they did a gate-set tomography, and based on that they did the noise model. But in that case, I suppose it must not include correlations, right? I doubt that could have done gate-set tomography on, like, what, 2 qubits is probably max anyway, right, Michał?
Yeah, I mean, possibly, yeah, but yeah, sure. Let's not interrupt Frederik.
Sure, yeah.
I was just wondering.
But I guess it's also interesting for Frederik, right?
No, surely. I think, yeah. I mean, usually, yeah. I mean, you have some restricted error model, which then in itself is not entirely realistic. But I think what I also wanted to stress that this is intuition. Like the optimizer will probably in some way, I mean, just by trying to find the minimum, will steer away from parts where the quantum computer creates problems. But I think this is, I mean, also very limited. If you have an extremely noisy device, it just won't work. That's for sure.
Sure.
Yeah. Okay, then let's talk a bit more about optimizing these parameterized quantum circuits. So, and I will just mention a few things that people have done and studied, and yeah, feel free to ask me or ask me later about this in more detail. So there's a variety of zeroth order methods that people have studied, and then I will come to first order methods and maybe contrast them both a little bit. So one thing that people have looked at, and that's quite interesting, is the simultaneous perturbation stochastic approximation, SPSA, together with Adam. So this is this adaptive momentum optimizer that you might know from machine learning. So I think it's one of the most popular machine learning optimizers where you give your gradient descent some momentum, which often avoids a lot of problems that you have with plain gradient descent or similar things. And RSGF is randomized stochastic gradient free method. I think it's pretty similar. The idea is that you get something like a pseudo gradient by evaluating your cost function at two somewhat random points, and then you calculate the difference between those 2 points and use this as a very crude approximation to your actual gradient, which you don't have access to. And this, you can always use this when gradients are or cost function evaluations are not for free, which is the case in for many quantum circuits. That's the case. And yeah, people have done this, and in some regimes this was also shown to be successful. So I think it's funny because it's a zeroth order method. At least, I mean, this one explicitly says it's gradient free, but then you combine it with this Adam optimizer, which is a gradient optimizer, so to say. But that's quite interesting.
Sorry, Frederik, can I bump in here for a second? Okay, in the first slide, you somehow, sorry, like some ant attacked me. So anyway, so you in the first slide, you didn't emphasize the fact that like when we query quantum devices, we actually have access to samples only, like not to expect. I mean, you emphasize some expectation values, but of course we have like estimators, and we can just query our device just finite number of times. Yeah. And in that respect, so those methods they should take as input like more like estimators of expectation values rather than. So are there like designed to begin with to work with estimator. Sorry, to work with
yeah, I mean, I think I will come to this, and maybe otherwise let's discuss this again if I don't say the things that you were looking for. But yes, this is kind of one of the key observations that led to us going into more detail and writing this paper. Yeah, I will discuss this. Okay, but yeah, let me finish those zeroth order methods and what people actually have done in those, as far as I understand, is really they calculated estimators to the expectation value, and they did this to some accuracy and then treated them more or less like expectation values. But what you, on top of that, what you have, for example, in SPSA is that this gradient estimate is super random anyways, because you have this random, you just use a classical random number generator to calculate these shifts, and this is introduces a lot of randomness a priori. So even if you calculate expectation values to high accuracy. Okay, so then swarm optimization is something that I found quite interesting. So the idea is that you evaluate your cost function at different points in your landscape, and then you have some, based on the values that you get there, you have some dynamics between those points, and then this behaves like a swarm and it tells you at which, where these points sort of move, and then you evaluate your cost function again at these points. And for certain problems, this also worked quite well. Genetic algorithm has also been studied. It's quite interesting. It's a very powerful optimizer for, I would say, hard problems in a reasonable number of parameters, but not too many. And what I actually found interesting, so this is also fairly recent. These people have written some software package which they inspired by the scikit-learn software package have called Scikit Quant, and what they have there is 4 optimizers, and there are gradient-free optimizers for quantum circuits, and they explicitly take into account that this cost landscape is very noisy because you're working with NISC devices. I didn't list these optimizers that they have in there because I think you just, to me, they didn't say anything, but they sort of identified 4 optimizers and argue that those are particularly well suited for noise. And, yeah, interesting if you encounter problems like this. I think it's worth looking at it at least. One thing that I took from looking at different zeroth order optimizers is that I think it's fair to say that they work well up to a certain amount of parameters. And when the parameter landscape or the parameter space becomes very huge, high dimensional, then they're starting to really struggle. The highest number that I encountered in these studies was 300. And I think that's probably already quite optimistic, but I'm not sure. It also depends highly on the problem. But we also know from classical machine learning that once you go to a really large amount of parameters, as long as you have some access to the gradient is extremely powerful and will always outperform zeroth order optimization. No one would start and try to optimize deep classical neural networks with zeroth order optimizers.
Sorry, just a comment. Because it's implicit in what you are saying, like zeroth order methods are the methods that work with, let's say, estimators of quantities you are interested in optimizing, as opposed to computing or estimating derivatives. Just so people. So sorry. Yeah.
Yeah, no, that's exactly it. I think we've also had some discussions internally in the group sometimes what zeroth order and non-zeroth order is. You can always get the gradient by evaluating the function at sufficiently many points, but then that's not really a zeroth order method anymore because you're really trying to get the gradient. So I think this also depends a bit on your definition. Okay, so that's why we were interested in first order methods and gradient-based optimization. So this is what I'm going to talk about today. And just to remind you, I mean, gradient descent, what it is. So if you have some loss function in your cost landscape and you sit at some point, then you evaluate the gradient of your loss function with respect to your parameters. And then you walk in the opposite direction. So you subtract from your parameters your gradient with some factor, which you call step size or learning rate. And if this was chosen appropriately, the learning rate, then you end up at some point where the loss function is smaller, and iteratively you get closer and closer to your local or global minimum, depending on the loss function. Okay, so how do we do this? Like for first order optimization, I think this is crucial for quantum circuits, parameterized quantum circuits. It's crucial whether we are able to obtain good enough estimates for the gradient efficiently in order to answer the question, like, should we do gradient-based optimization or not? And one of the problems is that the gradient is expensive in some sense for parameterized quantum circuits, because we don't have something like the auto differentiation tools for classical functions. We cannot just differentiate quantum circuits on a quantum computer, because what you have to do for that is you have to store intermediate stages of your computation, and this, by the no cloning theorem, is impossible. But the good news is that the exact gradient is accessible. So the exact gradient of these quantum circuits can be computed, and exact in the following sense. If your loss function consists of an expectation value with respect to this output state of the parameterized quantum circuit, then you can really get in terms of these expectation values, you get the exact gradient. So one of the methods is writing the gradient as a circuit. And this is not the method that we've used, but I found this quite interesting, and I thought it's nice to be aware of this. So you can write the gradient of some quantum circuit or of such a cost function as a circuit. This is done here in this work. So the way we do this, we split our circuit into two parts. So first W and then V. And this is the output state. And so what we're interested in right now is this gate, e to the minus I theta x, which sits in between V and W. And we want to differentiate with respect to theta. And the way we do that, we write down the loss function, and we have our parameter appearing twice, here and here. And so if you calculate this, then you get this imaginary part of this expression. So what you see then is that this is essentially, I mean, this is the output state modulo like one additional gate that you have to apply. And then you also have your observable that you have to apply here. And calculating objects like this is or calculating imaginary values of inner products is something that you can use the Hadamard test for. So if you know the Hadamard test, you probably know it's used for computing imaginary parts and real parts of inner products. And the way this circuit looks, so it would take a few lines of calculations to show that this circuit gives you, in fact, this imaginary part. But I mean, what's remarkable about this is that you essentially just apply. So this is your computational register, and then you need one additional qubit. And on your computational register, you really just apply W and V. So this was the original circuit, plus this extra gate that comes down as a result of the differentiation. And you have to apply this in a controlled fashion. And here on the ancilla, you also have to do this Hadamard gate and phase gate in order to get the imaginary part. And then you measure in a set basis here on the ancilla, and the rest you just measure in your Hamiltonian. And yeah, this gives you the exact gradient as long as you have this, like, measure this sufficiently many times to estimate an expectation value again. Okay, And the alternative that you can use, which I think is a bit easier to remember, but I mean, I think they're comparatively in performance, both methods, is the parameter shift rule. You might have heard of it, which expresses the gradient of such an expectation value in terms of expectation values as shifted parameter values. Okay, so if we're differentiating again with respect to theta, and theta is the angle of a Pauli rotation. So something like this here, the e to the minus I theta x, and x is, say, a Pauli gate, then a Pauli matrix, then we only have to shift our parameter by pi over 4 and minus pi over 4, and the difference of these two values gives us the exact gradient. Okay, so what we see is also that this is the exact gradient as long as we have access to these expectation values. But yeah, this is obviously something that's not the case, as Michael already said. We can only estimate them. Okay. Yeah, so then maybe let's talk about this, the stochasticity that comes into this. And this is also what started our research for this paper. And I will shortly go through the few sources where stochasticity comes from. So the first one we've said twice now, it's like you have to measure a finite amount of times in order to estimate this expectation value, and there's some inherent stochasticity. What we saw people doing in several papers was use a huge amount of shots to estimate this expectation value. And our question was, well, can you just use one and still like get a very noisy gradient, but maybe it's still going to work, and or like it's still reasonably working? And this was kind of the question that we started with. And then we also got to several other aspects. So the next one being that your Hamiltonian might consist of several components which do not commute. And so what you would have to do then in order to estimate your expectation value, that you don't only have to measure like several shots, but you have to measure several shots for each component, right? Because you have to measure each component individually, since they don't commute, you cannot measure them at the same time. Okay. So this gives you a second option to introduce stochasticity in safe circuit evaluations if you just sample one of these components each time. And this actually works. We've also done this. I mean, it's another question whether this is really efficient, but you can save circuit evaluations this way. I will also say more about this later. So in the third case, let's go away from these simple expectation values. You might also imagine using expectation values as some output and then post-processing this more in some function. So in this case, you could just write down a mean squared error loss. So you take the output of your quantum circuit and interpret it as some prediction, as some label prediction. Okay, so the simplest example, I mean, this is so like as some machine learning examples. So you feed your input data that you have additionally now is pictures of cats and dogs, and then you have labels. So 0 for cat and 1 for dog, and then you feed the pictures into your quantum circuit, and the output should then be close to the true label, and this is captured by this mean squared error loss. You might also know this from fitting problems. And we've also done this numerically. Okay, so what you can do here is obviously use the stochasticity that you know from machine learning already. I mean, this is done every day. No one sums over the entire data set. People just use a mini batch of the data in order to evaluate your gradients. So this introduces more stochasticity, and this is also what the classical stochastic gradient is, right? Good. And then the last thing that you can introduce stochasticity and again safe function evaluations or circuit evaluations is the parameter shift. And remember, if you differentiate this this loss function, you have to shift this parameter by plus pi half, by plus pi half and minus pi over 4. And so you can just sample these terms. And if your gates are more complex, then you also have several parameter shift terms. And then you can save more by really just sampling one of these terms. So you can actually reduce the number of circuit evaluations per gradient estimation by quite a bit by making use of all these stochasticity or potential stochasticities. Okay, so a comment on this, like maybe like for also realistically, how realistic is this? It's not clear, I think, whether like using few measurement shots is actually something you want to do, because this could be hardware dependent. I think I've been told that in superconducting circuits, once you've set your parameters and you settled them, actually running the circuit 10,000 times is almost for free. Like it's very fast. So then you probably don't really have to care whether you do one circuit evaluation or 10,000. In other architectures, however, so cold atoms or things like optical lattices, it's like every shot takes a long time, and then you probably want to consider these kind of techniques. So this depends on your architecture. Yeah, again, I said this only makes sense sampling these components if they're not commuting. If they're all commuting, you can probably measure them all at the same time or on one state that you prepared. And here you get at least, like sampling these parameter shift terms, you get at least a factor of 2, but for more complex gates, you can actually save more. And I will come to this in a second. Okay, so this was just the loss function. For completeness, I thought I also write down the gradient itself, but this looks a bit ugly, so if you don't want to look at it, it's also fine. But so this is what the gradient of, if you have such a mean squared error loss, which we actually did in our numerical simulations, then you have such an object, right? You have to differentiate the square, then you get this object, and then here you get the inner derivative, and there you use the parameter shift rule, which okay, in this case it's pi over 2, which I think comes from a 1/2 in the gate. That's not important. Okay, but what we see is that we get several of these expectation values, which we all have to evaluate. And here we could sample one of these two terms. Okay. So maybe to demonstrate how like these parameter shift terms can help you, or sampling these, how they can help you or might help you in optimization. If we come back to QAOA, then what we observe in this particular ansatz, which is, I mean, used quite a lot, is these gates that we have here that are parameterized by these beta and gamma parameters. They consist of something that's very far from a Pauli matrix. Namely, so this X is a sum of all Pauli X matrices, and this H is some Hamiltonian, which involves many couplings between qubits. So this results in many small Pauli rotation gates. And if you have n qubits, this means you have 2 n parameter shift terms. And the same thing happens for the Hamiltonian. If you have m terms in your Hamiltonian and there are 2-body couplings, then you have 2 m parameter shift terms. It could be like, if it's a different Hamiltonian, then this might look different. But again, I mean, imagine like this n m, this can be quite an overhead if you have to, or if you aim for evaluating all of these terms. And so if you only sample one of these parameter shift terms, then per gradient estimation, you make you have a saving of 1 over n plus m circuit evaluations. So I actually wanted to try this and see whether this gives you a reasonable advantage, because obviously this makes everything a lot more noisy, and your gradient, the variance of your gradient estimator increases. But what we've seen numerically, at least, is that this actually still drives you in the right direction during optimization. I think this is what counts. Okay, so let me say a few things about convergence properties. And So the main thing is, if you ask, do we still have convergence, or can we still guarantee convergence? One thing that you need in order to guarantee, or to talk about, like to be able to guarantee convergence, is that the estimator for your gradient is still an unbiased estimator, right? And as long as you have these expectation values as your loss function, so simply the expectation value of your Hamiltonian as a loss function, then you know, okay, even if I only use one shot to estimate my expectation value, you still get an unbiased estimator. So an unbiased means that the mean of this estimator is the same as the expectation value. But if your loss function involves some nonlinearities, then this is far from true. So here x is some random variable. So this is our estimator for our expectation value, or you can also imagine it as the estimator for the gradient. And well, actually no. This is the estimator for the expectation value, because then we feed it into our loss function. And if this is nonlinear, then we have the problem that the expectation value of some function of some random variable is not the same as the function of the expectation value of the random variable. Okay, and we solve this for polynomial loss functions. For polynomial loss functions, you have to work a little bit, but then you can still guarantee that you get an unbiased estimator. And we actually came up with some like slightly complicated scheme to correct for this bias that you introduce if you do it naively. And then one of the referees pointed us actually to a much better solution using these fully symmetric estimators. So if you have a loss function that is a
sorry, Frederik, can you? I actually didn't get this point. So
yeah.
So I understand that when you have some quantity, some stochastic quantity x, like basically when you compute some functions, may not compute like this loss function L may not compute with like taking expectation values. So, but why do you where do you encounter this kind of problem? Yeah.
So so what you want is what you do in order to calculate your gradient is you evaluate loss function estimators, right? You get use loss function estimators, and you subtract them from each other, and using this parameter shift rule, and then you get an estimator for the gradient.
Yeah.
And so what you do is this side of the equation. But what you're after is
yes. Okay.
is this, right? We want the expectation value inserted into the loss function.
I see. I mean, so and then the problem is like, I mean, if the loss function is linear, then there is no problem, and then you are now discussing the situation when it's polynomial.
Yes. Yeah.
Okay.
Exactly.
Cool. Thanks.
Yeah. Yeah. No, it's good to clarify this. Also, I mean, what you see here is if you only have a square, so the simplest case, like a degree 2 polynomial, then here we have linear, like in the gradient again, we have it's all linear and expectation values, and we don't have to worry. So like the square is the one forgiving part where we can just do it naively and still end up with an unbiased estimator for the gradient. But everything that goes beyond the quadratic polynomial needs some corrections, or you need to work a little bit. And
so I maybe a stupid question, but is it like the more complicated loss function, then it's better, like in a sense that your higher order polynomials are here preferable, or it's not like that generally?
Yeah, I think you're asking a key question. I think like out of my head, I can't think of any loss function that you would be interested in that are not like mean squared error, except for things that are not polynomials, right? So the log likelihood involves a logarithm. And I think also, I mean, I'm not entirely sure whether this makes sense to use expectation values as probabilities. this, I mean, maybe this is a stupid idea, but at least it's thinkable to do that. And then you have the problem that this is not even a polynomial. And so maybe this solution that we found for polynomial loss function is useless in the sense that no one really cares about higher than degree 2 polynomials. But I think the only hope might be that you can also extend this to non-polynomial functions.
Sure. So just some comment in the quantum setting, sometimes people, let's say, maybe care about fidelities or things like this. Like those might be some other, quantities that are nonlinear, right?
Mm-hmm.
Like fidelity with some target state. But they are, of course, not polynomial, often.
But I mean, fidelities would be, I mean, fidelities are like, so if you look at overlaps, right? So you have some.
I mean, like, well, you have mixed states, for example. I mean, for pure states, it would be all right.
Yeah.
But, I mean, depends. Okay, but like also, like there might be like overlaps, but it will be then not a polynomial in those variables that you consider. Yeah.
That's, yeah. Okay, that's true. Yeah. Yeah. Okay. Well, yeah. I mean, I have to admit we haven't spent too much time thinking about like which kind of loss functions are really interesting. We just thought, like, I mean, initially we just wanted to find estimators, like corrections, so that you get unbiased estimators for any loss function you like, and then you can do it. But yeah, this I mean would also be very interesting to actually extend this and think about these things. Okay, yeah, I mean, let me briefly say how this works. If you have some polynomial loss function, so polynomial of kth degree, looking something like this, and what you do is you interpret this polynomial as a polynomial in multiple random variables, which happens to be the same random variable every time. And then you take your samples that you get, so you take k samples from your random variables. So then you at least have to take k samples to estimate your loss function, and you sum over all. So you enter those in all different permutations into the arguments of your loss function. Okay, so that's why it's called fully symmetric estimator. Okay. And yeah. Now there's one more thing that you might ask. I mean, this is all talking about like when are gradient estimators unbiased, but you might also ask, like, what can we say about the gradient iteration, the gradient descent process? Can we guarantee that it converges or not? And I think this is something that.
Sorry, Frederik. But so you're saying that this particular, let's say, estimator would work. This is what you. Okay, because this is it would like automatically like satisfy this equation that you wanted to be satisfied.
Yes.
Oh, because just to be okay, cool.
Yeah. Okay. And yeah, so and then you might ask, okay, I mean, what can we say about the whole process, the gradient descent? Will it? Can we guarantee that it will converge to the global minimum? And the answer is obviously, in general, no. I mean, if you have some generic function, you cannot guarantee that gradient descent will find a global minimum. But if you make like some assumption about the loss function, which are in some sense constructed, like this PL inequality, which essentially means no local minima, and you additionally have a Lipschitz continuous gradient of this loss function, then you can really write down strict bounds or like convergence guarantees. So you can say after a certain amount of steps, you are within a certain range of your global minimum. Okay, but this is more like you can read a lot of this here in this nice lecture notes. But I think, I mean, in the end, when you go to interesting problems, then your loss function never satisfies these properties, or it has local minimum. Okay, so then let me say some things about our numerics and our results that we did, because I think that apart from writing down convergence guarantees as theorems, it's also very interesting to see what happens in reality when you train these things. And what we also did again was to train. Like, we just simulated a pure state simulation, so no noise, just the unitary circuit. And one thing that we did was we took one of the classic machine learning problems and did this with a quantum circuit. So we embedded these MNIST handwritten digits into a quantum state and then trained the quantum circuit to distinguish those two. And in order to make it a bit easier, we downscaled them. So as you see them here, this is the way that we use them. And we only selected 3s and 6s. And then on top of that, we used batch size 1. So we had like classical stochastic gradient descent. And then on top of that, we used like various forms of like low measurement shot stochastic gradient descent. So it's really a doubly stochastic gradient descent. And then, yeah, so our quantum circuits had 400 parameters. And so what you can see here is the exact stochastic or exact gradient descent, in the sense like infinite shots. We really have access to the expectation value. And then you can see the accuracy going up quite quickly. And but I would say like more interesting is that even when you use very low, like high variance estimators for the gradient, like only one measurement shot, you still get quite high in accuracy very quickly. We not as quickly notice that here we have 10 epochs, and 10 epochs here are already the end of this whole procedure, but yeah, it's comparable. So I think this in this instance it worked quite well actually.
Frederik, can you elaborate a bit on this MNIST classifier? Like what problem? Like sort of how do you encode the data, let's say, in those?
Yeah. Now this is a really good question, because what we did, we cheated. We used so what we did, we encoded these images into our quantum state as the initial state. So we used for each training. So whenever we trained on some image, we used this image as the input state, so to say, for the quantum circuit. What you would do in reality, obviously, you would have to write down an encoding state, and this would increase the circuit depth, right? Because you first have to encode your image, and then you do the classification part.
But if you assume that you have perfect gates, then it's is this a difference? Like,
can you say this again? Sorry.
No, I ask if there is really a difference if you assume that you have no noise anyway.
No.
Right.
With no noise, you could also write.
It's not real cheating. So, just saying. Yeah. Sorry, Michał, you also wanted.
Yeah, just my question. So this encoding. So the number of qubits was such that just via computational basis state you could encode just like sort of exactly like those images, like in.
Yeah.
Okay. Just like in.
Yeah. I think here you have 8 by 8, right? 8 by 8 pixels, and then we also have 8 qubits. So we have 200 and 65, 56 dimensional quantum states, so to say, and we encoded the images into those states. Yeah. But you could still. We had some intern who was actually like quite keen to try this out and try to variationally encode data into quantum states as efficiently as possible. And yeah, I think amplitude encoding is quite challenging, but we took it for granted in this case. Yeah.
Sure.
But I think like the key message here is that like provided that you have some data in your states encoded, like whichever way you do this, the training procedure actually performs quite comparable. So like whether you use 1 shot or 10 shots or like 80 shots, not such a difference.
Please, Philip, sorry.
Okay, me first. Nice. No, I wanted to ask what is exactly this accuracy here? Like, because this is quite a different problem than standard quantum problems, right? With those images. So
yeah, I think that, So I think this is the amount of images that you classify correctly. I'm not like out of the top of my head, I'm not entirely sure. But this is typically how you, in the classical machine learning, this is how you quantify your model, right? If your model classifies 99% of the digits correctly, then you're sort of happy, and depending on...
Sure. Yeah, that makes sense. And so for how many pictures was that, more or less?
I think the MNIST dataset contains something like in the range of 1,000 or 10,000 images or something, and we've used a subset of those. I'm not entirely. I think we've used 200 for the training set and then 20 for the validation set.
Okay, cool.
Okay, so my question was about like what was this? Because it's pretty nice how like the dependence on the number of samples, right? It's still, you can train it pretty well in a single shot regime. So what was the circuit that was doing the classification? How complex it was?
Yeah, I will show you this in a few slides, and then I will also these 400 parameters. Yeah. Okay, then let me just briefly say, because we also did some other numerics, we did max cut, the maximum cut problem with QAOA. So maybe if you're familiar with these QAOA type algorithms, then you in this database. Okay, yeah, and I think we used something like 220 or 420. Okay, so yeah, if you're familiar with these Quora studies, and a lot of people look at max cut, and you will see why in a second. It's a combinatorially hard problem. The task is, when you have some graph, you can either see it as a coloring problem or like as the maximum cut problem. So the task is divide those edges into two groups, where the target is, or the objective is, to have as many edges cutting between those two groups. And you can also see this as a coloring problem. So color these in two colors so that as many edges as possible go across these colorings. So, oops. Oh, so yeah, for this small graph, that's quite easy. And we see that this edge cannot be cut, and this is the maximum cut that we can find. Yeah, and this is a hard problem, and so people are interested in how well does Quora perform on such problems. We cannot expect that it'll solve these problems exponentially faster than classical algorithms, but still it's quite interesting, because these problems also are relevant for real world applications. And how do you do this on a quantum computer? So what's the Hamiltonian? It's simply an anti-ferromagnet. So you panelize all edges that connect two qubits which point in the same direction. And here the graph that your antiferromagnet sits on is mainly exactly the graph of your max cut problem. Okay, so we picked a bunch of such max cut problems with 8 qubits again. So one of those you can see here, and solve those with the Quora algorithm and optimize those parameters. So here we picked p equals 50. And I think that's quite a large number of parameters for Quora. And most people are more interested in, like, if we have very few parameters, what can Quora do? Because I think there's reasonable hope that even for small depth, that Quora can already solve, get to interesting solutions. But here, the objective was to see how does the stochastic gradient descent perform on a large number of parameters. And what you can see is during the optimization, so this black line is the exact expectation values. So in some sense, like infinite shots. What you can see is it's simply counting by optimization steps. This is the fastest because the gradient has the lowest variance, namely 1, no variance at all, 0. And so it converges as fast as possible. And if you go to lower shot numbers, then it takes longer to converge. But then if you account for, if you account in your iteration axis, if you account for number of circuit evaluations, then this whole image inverts itself. And you actually see that the one-shot optimization decreases the fastest, and then the more shots you use, the longer you need to decrease.
So what is the cost function here exactly?
It's precisely this Hamiltonian that I showed on
so it's just an energy estimator, right?
Yes. Yeah.
Okay.
I mean, I shifted this I shifted this in such a way that 0 is always the optimum. So if we reach 0, then this means we found the maximum cut.
Right. Okay.
Yeah. So what we can see, so what we see here is also that, I mean, at some point when you get to like smaller and smaller cost function values, then your variance starts to become a problem. And then actually like these optimization schemes perform comparatively, although this was not always the case. So for example, this instance, like this is a bunch of different problems, and then you can see the cost function after 10,000 circuit evaluations. And what you see is that the one-shot results are always lower than the other ones. But even if you like allow these other ones to go much further, so in this instance, this one was always the lowest. So I mean, the high variance of this one-shot optimizer might also lead sometimes to it actually like getting into areas of the cost landscape that other optimizers wouldn't get into.
Sorry, I think I didn't get why there are multiple points with the same colors on this graph. Could you?
Because this is several runs. So this is like each of these columns is, each of these columns is one problem, like one max cut problem, like this one. Mm-hmm. And then the points in the column correspond to several runs because I mean it's a stochastic rate.
Of course. Yeah, I get it. Sure. Mm-hmm.
Yeah. Okay, so I mean, I think what we took from this is that the number of shots that you use during optimization is a hyperparameter, and you should think about how you choose it when you do optimization, but you should also consider tuning it while you optimize. So we were thinking whether it makes sense, for example, to start with with a very low shot number to decrease your cost function quickly, but then maybe tune it up at some point to allow to find higher accuracy in your minimum that you're looking for. Alternatively, you could also play around with the step size. We haven't really found a like very conclusive statement on this, but yeah, I think that this is the main message, that the number of shots is a hyperparameter. Yeah.
Frederik.
Okay, so Michał, you first, please. No.
Thank you, Philip. Thank you. So I wanted to ask what optimization method do you use? Because you have there like this optimization, like number of optimization steps. So do you sort of you go over like the parameter space, like those? I mean, whatever routine you're using, probably first order, right?
Yeah.
So like it updates parameters of the circuit like 10,000 times, or up to 10,000 times, as far as I see. Right?
Okay. So each of these steps corresponds to one gradient update, or like a gradient-based update. Mm-hmm. So we calculate a gradient in each step, and then we update the parameters. So we didn't do plain gradient descent in this case. We used Adam because it's just, I mean, we also tried gradient descent, but Adam turned out to work the best. Yeah. And so you can actually see also a bit of momentum in these. It's less noisy than the plain gradient descent.
Mm-hmm. Mm-hmm. Right. So I wanted to ask some specific technical question here. So because here you plot like what is the cost, which is the expectation value, right? Like this cost is the expectation value of the Hamiltonian. And maybe you also looked at the following thing, like when you got into somewhere with those parameters, with this one-shot optimization, what is the actual like expectation value there, not the estimator of it? Oh, that's what I mean. Sorry. Yeah.
I think I get what you're asking, but these are this is the exact expectation value. So like,
okay. So this is the I see. So now, So you plot what is like based on you are doing optimization based on estimators, but you plot where it is like in Platonic world, right?
Exactly.
Okay.
This is obviously something you wouldn't do if you do this on a like in reality.
Well,
if you really because then you wouldn't spend many shots to really get like high accuracy expectation value estimate.
Sure. So probably you would do like at the last step you would do more shots. Of course. Okay, cool. Thanks for clarifying.
I think this is also, this comes maybe down to like one of the conclusions that I had is that like when I saw people doing these optimization procedures and then I saw them trying to get very high accuracy during the entire optimization process, my intuition was always, I understand that you want very high accuracy because you might need chemical precision or these kind of things because you want to solve like these chemistry problems. But during optimization, you probably don't have to worry so much about precision or like the variance, right? You can go very crudely in the right direction towards the end. Then you care about precision, and then you can do your high number of shots or very small step size. But somewhere deep in the optimization phase where you're still going somewhere, you don't have to worry about that. Okay. Let me advertise very briefly the software that we've used to optimize to obtain these numerics, because we've written our own package, and I'm not saying that you should use it necessarily, but if you want to differentiate quantum circuits and either with the parameter shift rule or just get like plain gradients of quantum circuits, then you could consider this. So this is the package that we've written, gradient. And the nice thing about it is that you can talk to me and I will help you. But the bad thing about it is that I do other things now, and so it's also not. It's under construction and also not so well maintained. But it's easy to use. So you really just you have to clone this. You have to download this package, and then you can import your circuit like this very easily. And this is the circuit that we use to classify our endless images. So this comes back to the question: which circuit do we use? And this is what it is: random rotations. So we picked. For each of these rotation gates here, you have one direction. So either X, Y, or Z individually, and then the parameter that still parameterized this whole circuit, the parameters are the angles of those rotations. So this circuit would have 10 parameters because you have 10 rotations. In between, you have entangling gates. And then once you have imported those circuit, you have to specify like your observable. So your observable interactions, you just have to write this adjacency matrix here, and maybe the first and second qubit should have a anti-ferromagnetic interaction, and then the second and third one, ferromagnetic interaction. And once you've specified this adjacency matrix, you can construct your observable. Then you have to choose your axes. So this would be a 2-layer circuit. You do X rotation on all 3 qubits in the first layer, and then a Y rotation on the first and then the third, and a Z rotation on the second qubit in the second layer. And then all you have to do is create the circuit by passing this observable and the axes into your random rotations circuit. And then the method, this circuit has a method called gradient, and you also have to say at which angles do you want the gradient, and then you get the gradient expectation value. And to show that this actually works well, because we've spent some time optimizing this, you can go to quite deep circuits. And this is something, I mean, this is the reason why we wrote this, because at the time, so here's some alternatives, but at the time, all of those alternatives, at least as far as I could tell, were not available. So we were looking for something to do this ourselves. But as long as you remain like within 15 qubits, I would say, you can get gradients very cheaply. I mean, very cheaply being within 1 second. So you can actually optimize circuits within like a reasonable amount of time. And if you,
I mean, naively, are those like estimators of the gradients, like, or like a shot, like sorry, so it's like a simulator of a quantum circuit, right? Okay, cool.
Yeah. And this would give you the exact gradients, so no estimators. We also have functions or methods that calculate estimators, these parameter shift rule and noisy estimators, but they are more expensive because it's not so easy to do this differentiation. But nevertheless, we have it, and I think all of those packages don't offer this. Penny Lane might, I don't know. But they're also, I mean, very quickly evolving, and I'm intending to compare my code to those, but I haven't done that yet. I would be really interested to see whether mine is faster than this, because they're really like true. They're proper software developers. They know what they're doing, and on the other hand, I'm also very rigid. I'm just saying like, this is the circuit and this is what you can work with. So this allows me to be very efficient, but also not much to design for the user, so to say. The other thing that you can also import besides random rotations is QAOA. So if you just want to optimize QAOA circuits, this is also something you can do with this. And what you can see also, I mean, here, so 100 layers, this would already correspond depending on how many qubits you have. But if you have 15 qubits and 100 layers, this already is a 1,500 parameter circuit. So this is quite a large number of parameters that you can play with and see what you can optimize it to do, so to say. Yeah. Yeah. Again, it's under construction. If you really want to use it for real stuff, then maybe better talk to me or make sure that it does what you want it to do.
Sure.
Okay. So the last thing that I want to do is point to some related work. I'm probably also a bit over time now. I don't know.
A little bit, yes.
Just a bit. We are though flexible, and there are many questions.
Yeah, and also it's our fault mostly. So.
No, but it's totally fine. But it's just yeah, very briefly, I want to mention these 3 papers because they're very similar to ours. And then I'm mainly done. I have a bit of an outlook, and then I'm done. So this paper appeared a bit earlier than ours by John Knapp and a PhD student of Aram Harrow. And they also, I mean, they already wrote down a lot of the things that we observed. And I think in a slightly different language, they didn't talk about all these nonlinear loss functions. But they've already observed a lot of these things. And I think it's quite interesting. And what I think what's quite remarkable is that they create this rigorous separation in some sense between zeroth and first order optimization. So this really, I don't know, is some reason to believe that first order optimization, so gradient based optimization at some point could be the more powerful method to train these parameterized quantum circuits.
So is it a separation in terms like of convergence guarantees or?
Yeah.
Right. Okay. So may I like here ask maybe a little bit silly question here, but like what is really the difference between those two? Because well, I mean, if you do this like for shift parameter rule, for example, in first order, right? then you estimate expectation value in 2 points basically and calculate a difference. And now if you do those zeroth order methods like SPSA or Adam, then at some point you also do basically like gradient estimator, in a sense of you do with random displacement, let's say you do estimator here, subtract them, and then maybe divide by the difference, right? Or something like this. So what is maybe really a difference here? It's not super clear for me.
No, I totally agree with you, and I think that it's a bit difficult to even draw a clear distinction. They have the advantage that, or they make it easy in some sense because they talk about these oracles that they can query, and then they establish this in terms of like they have this oracle-based separation between zeroth and first order method, where they say if you have an oracle, access to an oracle which gives you gradient information, then you will always be able to converge faster. On the other hand, as far as I understand, they motivate these oracles with the existence of these Hadamard Test type circuits. So I'm not entirely, like at the moment I can't say exactly how they differ from simple circuit evaluations, more or less.
Sure.
Yeah. But I think, you're asking the right question. I think this is not far from clear, and it would be very interesting to establish this. Right. Does it make sense to calculate gradients? I'm not 100% sure about that.
Sure. Yeah.
Yeah. Then this paper is, almost simultaneously with ours appeared, and they, looked at this almost the same things, like these number of shots. Can you use few number of shots? And they also came to a conclusion that few number of shots is totally fine. You get the stochastic gradient descent. One thing that they did is also calculate some way, they provide some method to calculate the optimal number of shots per parameter. So like if gi is the ith component of the gradient, or the estimate of the gradient, then they suggest that if you take the variance, or the estimator of the variance of the gradient, and divide it by the estimator of the gradient squared, this gives you some vague guidance for how to choose the number of shots per parameters. And I think this is also something that is totally intuitive. If you have several parameters, some might be very important, so you want to spend a few measurement shots on them, while others are totally useless, and then you just use one measurement shot, or maybe none at all. I don't know. Yeah, and then by the same group, so this is Patrick Scholl's group. They quite recently published this optimizer, which they called Rosaline. I don't know what it exactly stands for. It also has some meaning, but essentially they discuss this in more detail, sampling these Hamiltonian terms. I mentioned this, that you can sample individual Hamiltonian terms, which you cannot measure simultaneously, and yeah, they discussed in more detail how to sample these terms in order to decrease the variance as much as possible. This is quite nice to read, interesting. Okay, here's a very brief outlook. These non-polynomial functions are still it's not clear how to construct unbiased estimators. We've only done everything for the parameter shift rule. Maybe these Hadamard test circuits could also be interesting to investigate. I don't know if there's different properties popping up. Yeah, number of measurement shots, I'm wondering, so there's this plateau problem that when you optimize parameterized circuits, you have plateaus where you don't really have any gradient information. I'm wondering whether these low measurement shot estimators help you escape these or avoid these plateaus, but I have no idea. This is a bit what I'm doing with this intern from Hong Kong now. And then lastly, discussing noise in these circuits, so like decoherence or like any form of like realistic noise would be very interesting. Yeah, but this we haven't looked at this at all. Okay, so then I'm finally done. Thanks for your attention. Again, you can find my slides here, and I'm happy to answer questions that are left.
Thank you.
Thanks, Frederik, for a very nice talk. Yeah. Right, we had quite some discussion during the talk, but okay, are there some questions to the speaker, comments?
This was also very long, so I mean, I'm happy. Also, contact me via email, or I'm also on Twitter.
Okay, so I have actually, okay, one question. So regarding, can you move back to your conclusions?
You mean these?
Yeah, so, wait, what I wanted to, this, let's say non-polynomial loss functions. So my question is, like, are there some rigorous results? Let's say, imagine that your estimators are biased by just a little bit.
Yeah.
Okay, just a little bit. Like, are there some, I mean, intuitively, then your optimization maybe in some sense shouldn't go far, like too far, like shouldn't be too much skewed, let's say. So yeah, so I do some. I mean, I'm asking because, for example, in the course, like the Adam Buland, Umar Fazirani, Pfefferman paper on this. Like hardness of something from random quantum circuits, they do actually, I mean, to the different fields, but still quantum computing, they do truncation of, like they use actually polynomial interpolation as like a method of to prove something, but they truncate exponentials, right, to some order, right, and then they control the degree of this truncation. So it's conceivable that for parametric circuit, you can maybe just expand this exponent up to some degree and be, you know, happy with it, you know, in practice.
Yeah. I mean, I think, I mean, like there's 2 points that are very interesting. So the one being that if you have a bias, this might mean that you're going in the wrong direction in your optimization, but maybe not. And this is also something that we thought might be interesting to look at. Like, what, even if you have a biased estimator, is this so bad? I mean, especially I think in the beginning of optimization, often you only want to walk roughly in the right direction. As long as you don't like have a huge bias, this could be totally fine. So I think this would be interesting to understand actually how detrimental is a bias. And then the other thing is, I mean, we have this other construction for polynomials and how to create non-unbiased estimators, and then this is kind of series based. I can show it to you, but it's a bit overwhelming, I think. So we evolved this loss function as a Taylor series around its expectation value. And then from there, you can, as long as this is a finite series because it's a polynomial, then you can create these unbiased, these correction terms, which make your estimator unbiased. And then this was some form of like a series-based estimator. And the question was like, can we kind of do this for infinite series? And can we sort of find the correction terms for infinite series? But like we weren't able to see this. I think this is not so helpful right now to show this, but I mean, we've done this and then we never really touched it again. And then we're also pointed to these fully symmetric estimators. But this could be interesting to go more into detail. I think accompanied also with discussing whether like how much of a problem the bias actually really is, because we don't know. I mean, it's always nice to have the guarantee that you're unbiased, right?
Sure.
Yeah.
Okay.
I have a question. Only one more out of curiosity. Like in your results with the max cut optimization, did you maybe also check other like routines than Adam, which are also gradient based, or not really?
Yeah, we did. I did gradient descent. So the plane gradient descent was definitely worse than Adam. Then what we also did is rate decay on a plateau. So as far as I know, some people do this. They optimize until a certain point. When you get when you don't make any improvement anymore, then they interpret this as a sign that your variance is too large, and then they halve the learning rate with the step size.
Okay.
And they do this every time. You have to define a plateau length, and we did that. And I think this was definitely better than the plain gradient descent, which is a constant step size. But Adam was definitely a lot better. I think Adam is just really good at compensating this stochastic noise that these estimators give you.
Okay, I see. Well, I mean, it probably depends on a lot of things also. I once was using Adam, and I found it worse than SPSA in some instances of but this is just like, technical stuff out of curiosity, because maybe you tried some optimizers in some problems, and I would be interested in details. We also like this problem.
Okay. Yeah, interesting. I mean, I also know, like, a good friend of mine told me that, like, whenever he doesn't know really what to use exactly, or when he doesn't want to fine tune all the hyperparameters, Adam is a really nice hammer to just throw at your optimization problem, and it typically works quite well without too much fine tuning. But I think this applies to neural networks and in other problems. This is not.
Yeah. Okay. Cool. Yeah. It's thanks.
No.
Okay. Any last chance to ask something to Frederik? Okay. If not, okay. Let us thank him again for the nice and very willing to discuss with us and so on. And a nice presentation, of course. Yes.
Thank you.
Thanks, Frederik.